G'day Bifrosters, back with the noises. Today we're going to finish up with Worley, and in the next episode we'll start looking at some of the more esoteric ones, as well as starting to get our interface together. This is a big project. So the only real change you probably noticed since the last lesson is I've added a pass node in here so I can switch these around really quickly. And I've also added this if attribute on the Worley noise. I've also changed the name to Worley, but we always knew it was Worley. What this if does, if you remember, if we come in here, remember this index where we were getting the nth closest in the array rather than the absolute closest? If that's set to 0, then it's the absolute closest, but you don't have to set it to 0. And you can get some interesting results both with changing that number, so this would be an F1, starting to look a little bit more like a gemstone, or even something like F4, which is a lot more complicated again. But the nice thing is you don't have to stop there. So we're going to go on to making our second Worley noise now. We're going to base it completely off this one. So much so that I'm just going to copy and paste it. It's got the same inputs and everything. It's going to have the same outputs. We'll just bring our little noise purple down here to cover it. And I'm going to call this Worley F2, and this will be another distinct noise on the interface. But what I'm going to do here, I'm going to allow for two different n numbers and then a bunch of mathematical operations to those two results. And that way you can get some really interesting Worley noise. And this is how we make things like alligator noise, a fairly good fake of sparse convolution, but not an actual sparse convolution, all that kind of thing. So what we're going to need to do is we're just going to need to take all of these and copy and paste them. Wow, did it do that? Just put them right down on top of themselves. That was kind of cool. And what I'm going to do is the only thing I'm going to change is I'm going to put this out here. I'm going to call this one F2. Oh, the other thing we're going to do today is change the way we do our distance metric as well. So I might actually do that first, but I can do that with the magic of editing, so we'll see how we go. So now I've got F and F2. Let's get a little bit more together and call it F1 and F2. So just to give you the example that everybody uses, if I subtract the first one to the second one, and right now that's not going to do anything because they're all the same, but if I change that to 2 and that to 1 and then pop that in there, so this one's done by taking the second closest distance and subtracting the first closest distance to it. And we'll just stay with subtract for now to keep doing interesting things. So what happens if I change that to 4? Now you're starting to get really interesting shapes. Maybe change that to 2. So you see, it's a really versatile noise, cellular noise. You can do all sorts of things with it as long as you are happy to do it in cells. So we'll try something else now. We'll try adding these two together and see what happens. Again, you're still getting quite interesting patterns out of it. And again, if we change it back to say 2 and 1, a little bit less detail, but you still get the idea. Presumably if I went 16 and 8, you'd start to get some really detailed stuff going on in there. And you do. So I think this is a good thing to build into our noise node here, is the ability to do different mathematical functions on these. So what happens if we have a multiply? What's a multiply going to do? You're going to put it in there, aren't you? Because I had something selected. I'll undo that. So yeah, I'm not blaming Bifrost today. So what happens if I multiply F1? by F2 and pop that out. Not tremendously much. We'll take it back to 2 and 1's not going to work, is it? But now you're getting quite a nice, almost crystalline structure here. And these, of course, these aren't floats, so what happens with 3? Again, what happens if we do 2 multiplied by 3? So this just enables us to get a whole bunch of use out of one noise node, which is great, which is absolutely great. So I think we'll try divide. Last call. And that's again giving you some very interesting looking stuff. Many square edged holes. Basically, that shouldn't do terribly much. 2 divided by 1. Of course, if I set that to 0, it should break. Yep, because dividing by 0 is sort of death to anything computery. So I think this is useful enough that we can actually put a pop an enum in here, which would give us and our users the ability to switch between these really quickly. So let's real quickly go and make an enum. So I'll need to go to my compounds directory, which is here, and we'll just grab one we made earlier of something else and make a copy of it. And we'll call this functions.json. Open that up. Very careful to make sure we give this a name. You know what I should do? I should check there isn't one existing already for this, because there might be. Because it's a pretty common thing to be doing. There's one, and it's rotation order. So, let's make one. We'll jump in here, and we'll give it a name. You of course aren't going to call yours Valhalla. You can call yours whatever library you want to put this into. And we'll call this M functions. No, just functions. Let's not get fancy. So we'll start with add. We should actually be able to put the symbols in. And it should still work. Although, you know, famous last words, and then we don't need these guys, and we don't need the comma. We'll just save that, and I will return after restarting Maya. Let's give this a save, and we're back. So now we should have our own little custom enum. There it is, functions. Plus, minus, multiply, and divide. Perfect. So of course we're going to need to do the old setup of cases. So let's build a compound. And we'll put that in, call it subtract. Bifrost is complaining that there's something not working, which is this, because there's absolutely nothing plugged into it right now, which is okay. It's nice that it looks after us like this and warns us of stuff, but we all know what we're doing. So it's the same as the last time we did an enum. We're going to make a compound that does all of our casing and if statements for us, because that way we don't have to like display it and have 4 different if statements working. So here's the first thing we're going to need to do. We're going to need to make a copy of that. We're going to need to make it equal, like so. Is that equal to that? Oops. Is that equal to that? And then this one becomes our main menu choice. So we'll put that in there and we'll hook everything up. And then it's just if so. This is add. If it's add, if that's true, then we use this guy. Perfect. Now it's just a lot of copy and pasting. So we change this one to subtract and we hook up subtract to there. That gets into the false. So if it's not add, is it subtract? Paste it again. Change this one to multiply. Hook up the multiply result. Break the hell out of that connection because that's going to just break everything for us. Trust me, traveled that road before. Last one. And this will be the divide, so is it divide? If it's divide, use that. And then that goes into false. And then we are outputting whatever data is chosen. That goes into the set range and it stops being unhappy. It might even display something for us. Lovely. So right now what we're doing is we are going, okay, let's go for the classic 2-1. And in our functions we'll change that to subtract. And there you go, we've got our nice blunted sort of dragon fruity spikes kind of going on. Dragon fruit. Not even dragon fruit. Doesn't even look like a dragon fruit. I don't even know why I called it that. So this menu is something we're going to need to put out on the input. So, and of course, all I've got to do is quit Maya, and I can go back into the JSON and change these to the names. But for now, this is good. So this one node with this one addition, turn that on so we can see our feature points. Maybe. Are they inside? Have they disappeared? They might have. So I'll go up one, turn them off, turn those ones off, turn this ones back on. Nope, there they are. So that's showing us where our random Worley points are generated. That's nice. I wanted to make sure that worked. So just with this one node, we're now able to do a whole bunch of things. So if I say double the frequency to 240, give it a minute. Now we're looking a bit more sort of maybe dragon fruity, not entirely sure. Some sort of strange chestnutty thing anyway. And then I can go ahead and change what we're doing inside of there and we get a completely different look. Still complex, still interesting, still able to be used for something. The imagination is boundless, but it's all contained in this one node and you're able to do very, very quick things with it. Alright, so that's our Worley F2 knocked off. We'll leave it back at the classic. F2 minus F1. We'll get our frequency down. When we build our interface properly, which is going to be an episode all by itself, this thing is a big, big node. And it's kind of the price you pay for getting a high level out. Then we'll be able to hook all of these things up nicely. So that, but in this case, this has knocked off another noise. Happy with that. Let's do the distance metrics. So for that, we'll come back into Worley, and I'm not going to make the same mistake I made last time, and just, I'll plug that in straight away, and we've got our nice Worley noise back, and if we've got our color display back, we do, because that's looking a little harsh. So we'll turn that off. That's better. Still a little bit circular, but that's all right, we can live with that for now, considering what we're using it for. The color is just an indicator. So, in terms of this, so this is the best website I've found that explains how to calculate the different noise metrics. Right now, we are using this one, Euclidean distance. So, the distance of b minus a is equal to the square root of x2 minus x1, this is in 2D, so ours would have a z as well, x2 minus x1 squared plus x2 minus y1 squared, and in our case be z2 minus z1 squared. That's how Euclidean distance works. And that's just what we're doing by the subtraction and everything that we're doing. We've got two more. We've got Manhattan distance and we've got Chebyshev distance. So let's go ahead and get those creating. And we can, what's really nice here is that this is an interactive Voronoi generator, which at the moment is showing us Euclidean distance, and we should be able to add new points wherever we like. So we go to Euclidean distance, it doesn't change. That's what Euclidean distance looks like. Let's try Manhattan distance. Now you've got straight lines and 45-degree angles. Chebyshev distance, you've got diagonal lines mainly, and angles. So let's get these into our Worley. And we'll just keep this up because it's very handy to do. And where we calculate our distance is in these for each loops. I believe. Yep. So there's our distance there. So it's one vector minus another vector. And inside there, inside the distance between 2 points here, is this equation being worked out. So we basically need to give ourselves options on that. We need to do, well, let's do Manhattan first. So what this means is, I believe it's the absolute value of these two. And this is the maximum of the absolute value of these two. So let's go with, we'll just rename this to Euclidean. We'll make our own compound. We'll call it Manhattan. So you get Euclidean for free. Everybody's happy. We'll get our output in here. Pause. So this here, even though I've called it distance vector, is a subtract node. If we come back to our website, that's this subtraction here, b minus a. So all we need to do, I should think, for this one, we can completely break this down to its component points. Let's do that just to see. So we'll go one back, and instead of bringing in the distance vector, which we get for free, we'll bring these in here. We'll just call this one B and this one A. So we can do a little bit of math practice as we go. Okay, so essentially what we're doing is we're trying to get the absolute value of each of these. So let's split this up. Vector 3 to scalar. There we go, we've got X, Y, and Z. And we'll just do that again for B. So let's have a look at our equation. X2 minus X1, so the B's X minus A's X. So this is, yep, let's do some naming. That's B, that's A. We do a subtract. So we're basically subtracting A from B and then absolute value. And then of course we've got to output what we put in, and what we put in was two vectors. So really what we're going to need to do is output one, as per the equation, we're outputting one distance. So we're going to need to add all of these together at the end. So we can just copy this and do the Y. So BY and AY, absolute value. One more time. BZ and AZ, absolute value. And we just simply add all three of these up. And that should give us the Manhattan distance. We can test this by just plugging that straight in there. And you can see the difference. And I hope you can see the difference. Yep, you can see the difference in our Worley noise. So that's Manhattan done. And Chebyshev is the same, except for one thing. I think that's how I probably misspelled that. No, I did it right actually. I did okay. This is just the maximum of these three. So instead of this add node at the end here, we can quite happily just put in a max, plug all three into it, and then put that into the output. And we'll come back out and we will check that one. And that's changed us again. So it looks a little bit different than this does, but it does also have similarities. If we were to go front on, you see this is Chebyshev. It's mostly diagonal lines. You can see the little straight lines where they meet. The resolution is not very high on this model, but you can kind of see what's going on, and it does change the look. So to complete the whole thing, we just need to do a switch. So what's really nice is I have already done this. So we don't have to go off and make another enum this time. I've already got one. You might have to go off and make one, but I'll pop it up on the server for you. What did I call it? That's the interesting thing, right? I believe it was distance. Let's have a look here. Euclidean, Manhattan, and Chebyshev. Perfect. So once more, we'll break this, thereby breaking the entire world. Make a new compound. Pop these guys into it. Just give them some name so that I can not have to jump up and out to check what I'm doing all the time. We need a couple of these, one of which is going to be our selector. That's the same as before. We'll do this really quickly. Do an equal is what's coming in, equal to this thing. If statement. If that is true, then we are requesting Euclidean. That goes into the true case. That goes out. Everything stays broken because I need to hook that up to there. There you go, that's now Euclidean. 1, 2, oops, not that one. 1, 2, 3, copy those, paste them down. Get everything nicely laid out. This over a bit. This changes to Manhattan. This goes into the false. One more time. Oh, and let's not mix this up. That goes into Manhattan. This goes into the Chebyshev. Let's break that because we don't need that. It's just going to make our life more difficult and miserable at this late hour of the evening. Pop that into the false case, and we just need to change that to Chebyshev, and we're done. So now I should be able to use this menu to go from Euclidean to Manhattan. Yes. And there on to Chebyshev. Perfect. So by doing that, and we're fairly deep in the bowels here of the Worley noise, we're what, 5 levels down. But by doing that, we have now set up our distance metric. And all I need to do is, just with everything else, is I just need to keep promoting that up until I hit a top level. We can pop that there. And when we come right out to the end of the Worley noise, at the moment it's set to Euclidean. Let's set it to Manhattan, see if everything works, and it does. That's lovely. We want to do the same thing in our F2 Worley as well, which fairly easy because they both use this for each note, so I should just be able to grab that. So the only difference is, of course, that the Worley F2 uses it twice. So I'm going to paste it down twice. See, it's automatically hooked things up for it. And I'm just going to rebuild the connections as I go. So that one goes out to there, and this one goes out to there, and we can now delete these two. And now we'll pop our distance metric out. I'm going to look like an idiot when this doesn't work, but I'm fairly sure it will. Fairly, not 100%, never 100%. So make sure our metric set to Euclidean to start with. We'll pop that up there. Wait for this to change. Nope, it broke. Something in there did not like that at all. Did not enjoy that one little bit. Oh, I think I know why. There we go. Yeah, so it was, they were both coming from F1. I needed to make sure they were split out. So now the big test is if I change this to Manhattan distance, what happens to this? There we go. So that was nice and easy. If I change it to Chebyshev, changes again. I have no idea what that's supposed to look like as a Chebyshev, but that is kind of interesting. And don't forget the sphere is reasonably low resolution, so we're not going to get the best of ideas. But however, I do believe that if I go one back here, I made a switch. I made a switch that would allow me to turn this into a plane. So let's have a look at it on a plane. That, to me, looks like it's input number 2, which of course becomes input number 1 in the wide world of arrays. There we go. That's looking a bit more better to look at, and you can see that it's got that diagonal and intersection thing going on. Come back in here, change that to Euclidean again, see if we get our classic Worley. We do. Manhattan one more time, and again we've got that nice square broken up. So it's added another Worley noise. It's very, very versatile and allows us to do all kinds of things just with one noise node. You can start making really cool looking patterns like that, and don't forget this is 3D, so you can do 3D things with it if you want to. We also added our noise metric so that we can use Euclidean or Manhattan or Chebyshev or whatever we like. So that's pretty much going to be the end of this episode, I think. Where do we go from here? This noise thing is dragging on a bit, isn't it? It really is, and you know, it takes me a while to get new episodes out. So you know, bear with me. I'm going to get it finished. What I want to do next is I want to start looking at sparse convolution noise. That may, of course, not be possible because I'm having lots of trouble understanding it. And if anybody knows how to make sparse convolution noise, please get in touch with me, because I would love to know how to do that. I'm slogging my way through some of the papers on it at the moment, and I'm learning about Gabor kernels and 3D multiplication and vectors and dimensions. So that's great. That's the last noise I really want to put in, I think. After that, we go on to adding details. So what I think I might do is, now that Worley is complete, so our cellular noise is complete, I might go on to details next. So how to add terrain-like details to this stuff and all of that kind of thing. Then put on an interface, and then if I can learn how to do it in time, I'll circle back to sparse convolution noise, because we've set this up in such a nice modular way. Let's just pull that out of the noise box for now, that we can mix and match these noises if we want to, because even with this guy here, because we've did all the setup at the beginning, we can go to his layer editor and we can still change his amplitude, and it still goes to -5 to 5, to. I'm not sure we've hooked up the seed for the Worleys just yet. No, we have. So presumably if we change the seed, the pattern will change. Perfect. So yeah, I mean, the Worleys don't respond to the frequency or phase of the other ones because they're built a different way, and the phase we could add by just moving the Worley feature points around, which is, something we could look into as well. If anybody has any requests or suggestions with noise while we're doing this, the thing we're going to do after adding the terrain is adding masking, which is the thing that the Houdini Mountain note doesn't do. So I'm going to show you how to use one noise to mask another, which will be kind of cool, because then you can have flat areas, or whatever. If you're building terrain, you can have flat areas like lakes, or you can have depressions, or whatever you like. Alright, so hope that's helped, and I'll catch you next time.